Hello, my name is Russell, and today we will dive into a brief history and analysis of the composite materials used in helicopter rotor blades. The information presented was compiled by myself, Arielle, Alicia, and Janet. We will start with an introduction to helicopter rotor blades. We will then move on to the performance requirements rotor blades must face, followed by the developing history of material selection. A more in-depth look at the design considerations is explored, as well as the manufacturing and processing techniques used to execute the design. We will finish with a characterization of the quality control systems used for rotor blades, followed by a cost analysis. Igor Sikorsky invented the first helicopter in 1939, and the manufacturing process and materials have been improving ever since. Helicopters are utilized for a variety of reasons, including firefighting, crop dusting, military operations, and many other applications. Helicopters typically have 2 to 6 blades attached to the hub at the top of the fuselage. Each blade is made of a composite sandwich structure with a lightweight core and 2 skins. The other components of the blade include the leading edge and trailing edge spars. Many factors such as operating environment, materials, quality control, and more must come into consideration during the manufacturing of a rotor blade, as reliability of engineering and aerospace applications is a major concern. The design and quality of the rotor blade composites is of utmost importance because they undergo extreme conditions, including a very wide variety of temperatures and humidity during operation, from the desert to Arctic conditions. Additionally, during rotation, the blades flap in the vertical direction, meaning materials with good flexural modulus characteristics must be considered. If the helicopter is used in marine rescue operation, it may also experience degradation due to salt from the ocean. For these reasons, only advanced forms of composites are selected in the design of helicopter blades.
In order to understand what materials were selected for our helicopter blades, we needed to look at a brief history of the material selection overall. Up until the 1950s, wood blades were mostly used in the spar and ribs of several different types of woods with a fabric skin covering. These materials tended to absorb water. In order to mitigate this, wood blades were replaced by steel and aluminum blades from the 1950 to 1960. Although metal blades were easy to manufacture, they had a limited lifespan based on flight hours due to fatigue and repetitive loading, as well as a low strength-to-density ratio. Additionally, this material could experience catastrophic failure without warning if there was a crack. The next design advancement came in 1960s when a honeycomb core was added between 2 metal skins to replace monolithic metal blade. Such a change increased stiffness while decreasing weight. This original sandwich structure design allowed for higher performance due to better blade shapes as well as increased beam strength. These blades then advanced even further with polymeric composites. Metal skins were replaced with fiberglass skins with a foam or honeycomb core. Then, in 1971, PMI foam began to be utilized as the foam core with the purpose of decreasing corrosion and increasing the blade service life. With a foam core instead of a metal blade lives increases from 400 to 500 flight hours. More specifically for tail rotor blades, the cost decreases by 80% with honeycomb blades due to fewer curing and bonding steps. So for our helicopter blades, we chose to do the industry standard, which is a sandwich structure usually made of honeycomb core sandwiched between 2 fiberglass skins produced by pre-preg layups. The core material can either be light foam or an aramid or metallic honeycomb. Composites have better fatigue life properties than metals, but a significant disadvantage is that composites are more labor-intensive to manufacture than metal blades. There are also many high upfront costs, but composites of sandwich structures provide high reliability overall. Materials used today in industry include fiberglass or carbon fibers used for the outer skins and stainless steel spars. The use of carbon fibers or glass fiber reinforced polymer composites in rotor blades decreases the weight when compared to aluminum and dampens the vibrating nature of the blade during flight. Also, lightweight blades can increase fuel efficiency and payload carrying capability. Glass fibers, while on one hand have good strength and chemical resistance, carbon fibers have higher stiffness. 2 common examples shown in these 2 pictures are Van Horn aviation, carbon fibers, and epoxy prepregs are used. These fibers reinforced prepregs are laid on rotating angles, creating directions of differing strength and resistance to crack propagation. Another specific example of a blade made by Northwest Helicopters are used in Bell 205 helicopters is made of carbon fiber spar, Nomex honeycomb core, carbon fiber skin, and stainless steel leading edge.
The two main design requirements for rotor blades are high torsional stiffness and good lift-to-drag ratio. It is also necessary to have low electrical resistance on the skin, as a lightning strike would damage the composite blade. There are also different design requirements for the different parts of the sandwich structure. For example, the face sheets need stiffness to withstand tensile, compressive, and shear stresses. On the other hand, the core or filler needs a high shear modulus to prevent buckling along with sufficient stiffness. It also needs compressive strength to prevent crushing due to normal loads. Pre-pegs can be stacked with specific orientations, making sandwich structures anisotropic, and allows engineers to design parts with specific strength properties in desired directions. Because stacking is required for anisotropic properties, manual layup is the most common manufacturing method for the skin. Other advantages of composites over metals include that composites can have tighter tolerances than aluminum, and carbon fiber composites can resist dents that can adversely affect metal blades. The diameter of the curvature can be optimally designed to resist dents and improve flying capabilities while also preserving mechanical properties. Military helicopters with standard operating procedures have two blades where the total length can range from 35 to 48 meters long, while helicopters with specialized capabilities, such as Black Hawk helicopters, have anywhere from 4 to 7 blades, and all blades are over 50 meters. Seen on this slide is a flowchart starting from commercially available materials to the final part. The spars, skin, and core each have distinct starting materials with associated manufacturing techniques. After steps of quality control, they are assembled into the final blade with adhesive layers. Filament winding is the manufacturing process used to produce the spars, or the backbone structure of the helicopter blade. In filament winding, continuous resin-impregnated filaments are wound around a rotating mandrel from a linearly moving cart in order to create a part with an asymmetrical hollow core. Small and medium blade skins are produced through manual wet layup, where the fibers are in a fabric, mat, or roving form and impregnated by hand with resin. The blade skins are laid up in open molds and cured. Manual layup is labor-intensive and quality can vary depending on the worker. Additionally, fiber content can be hard to control, resulting in weight and balance issues. To improve quality, one can vacuum bag the product. Another layup technique that is used to make rotor blades is pre-preg layup, which enables the worker to better control fiber content and tends to contain less voids since the material is heated and pressurized during curing. Larger blades are mostly made through filament and tape winding. This process produces a hollow tube-like structure which is needed for the spar but is limited in fiber orientation and thickness. It is advantageous though because it is high quality and has low labor requirements as it is an automated process. If creating the sandwich structure out of aluminum honeycomb, the core is cured onto the skin with steam prior to excess material being removed. The advantages of using this structure include high ratio of bending stiffness to weight compared to a monolithic material, high fatigue resistance, good dampening, and increased thermal insulation. But there are also disadvantages, such as moisture getting trapped in the core leading to degradation. Quality control of helicopter rotor blades is of much importance because of the stress and loads the blades have to bear. Out of the mechanical properties of the part, fatigue strength is one of the most important characteristics. While there are many fatigue tests available in the industry, testing of the helicopter rotor blades are more rigorous, automated, and reliable to increase production rate of the blades. Visual inspection, infrared thermography, and wind tunnel testing are some of the common industry-established testing methods for blades analysis. The automatic chirography inspection system is the first such system developed to allow 100% inspection of the blades. Seen here is the cost analysis divided into operational and capital costs. The upfront costs are substantial, totaling $120,000. Of the recurring costs, the materials take up the largest percentage at 40.8%. This is expected since primarily advanced composites are needed to provide the performance capabilities required by helicopters.